Welcome to the deep dive. Today, we're really getting into the weeds, putting the standard heliocentric model, the one we all learn, under a pretty intense microscope.
Hmm.
Our mission, based on this, rigorous analysis someone shared, is to check if the core ideas about Earth's motion actually hold together logically, using first principles.
That's exactly it. We're looking at sources that use basic geometry, fundamental physics, and apply them very strictly to the standard story.
Okay.
And they claim to find, well, some pretty significant contradictions, logical problems, even right at the heart of how we describe Earth's axis and gravity's effect on its orbit.
Right.
So just to be clear, our aim here isn't to, debunk anything, but really just to lay out these deductive arguments, to show where the internal logic might stumble a bit, according to these analyses.
And these claims, they're genuinely surprising because they challenge things that feel like basic science facts, stuff you learn early on. We've got two big ideas to unpack today. First, this claim that Earth's supposedly fixed axis is geometrically, incompatible with how we explain solstices.
Yeah, that was interesting.
And second, the argument that the common explanation for why Earth speeds up and slows down in its orbit, that it's actually dynamically incorrect, based on fundamental physics.
Right. Mischaracterized.
Okay, let's jump straight into the first one then, the geometry. This fixed axis paradox, let's call it.
Sounds good. So we have to start with the standard picture, right? Earth spins on an axis. It's tilted about 23.4 degrees relative to its orbital plane, that flat path around the sun.
And that tilt explains the seasons. That's textbook stuff.
Exactly. And the crucial assumption is that this axis stays fixed in its orientation, pointing towards the same distant stars, basically, like a gyroscope wanting to keep its orientation.
That makes sense. Conservation of angular momentum, right? It keeps spinning the same way unless something pushes it.
Precisely. That fixed orientation is key. But now let's bring in another geometric piece, the solar terminator.
Ah, the line between day and night.
Yep. And the geometry here is pretty straightforward, according to the European Space Agency definition even. Sunlight comes in, effectively parallel rays lying in the orbital plane. The terminator line, the shadow edge, is always at a right angle, 90 degrees, to those incoming rays.
Okay.
So if the rays are in the plane and the terminator is at a right angle to the rays.
Then the terminator must be at a right angle or normal to the orbital plane itself. Okay, I saw that. Like the shadow line stands straight up from the flat orbital surface.
You got it. Now, here's where the solstices come in. For the standard explanation of solstices to work maximum tilt towards or away from the sun, the Earth's equator needs to align perfectly with that terminator line.
Right, so the longest day happens when the equator lines up just right with the day-night line?
Exactly. But think about the geometry. The axis of rotation is always perpendicular 90 degrees to the equator. So if the equator has to align with the terminator at the solstice, and the axis is perpendicular to the equator, then the axis must end up being parallel to the terminator line. But we just established the terminator is at a right angle 90 degrees to the orbital plane.
Oh.
So if the axis A must be parallel to the terminator T, and T is at 90 degrees to the orbital plane, P.
Then the axis A must also be at 90 degrees to the orbital plane, P, which means zero tilt. The 23.4 degrees has to vanish.
According to the strict geometric deduction, yes. At the moment of solstice alignment, the axis would need to be perpendicular to the orbital plane. It would require a reorientation of, the full 23.4 degrees relative to that plane.
Wow. Okay, wait. But that clashes directly with the other core idea, doesn't it? That the axis is fixed relative to the stars.
Exactly. That's the paradox presented.
How can an axis that conserves angular momentum, that stays pointed in the same direction in space, suddenly swing 23.4 degrees relative to the orbital plane twice a year?
It can't. Not without a cause.
That would need a massive external twisting force, a torque, right? Something we haven't observed acting on that scale that quickly.
An absolutely enormous torque. And it would have to act, then reverse, every 6 months. We know the sun's gravity pulls through the center of mass. It doesn't exert a net torque that could do this.
Right. Gravity pulls it around the sun. It doesn't twist its axis like that.
Precisely. The torques we do know about, like from the moon on Earth's bulge, cause the very slow 26,000-year precession, not this rapid, twice-yearly snap.
So this is a direct contradiction derived from the model's own geometric requirements and physical laws. How does the source explain why this isn't common knowledge? Why do diagrams look like the tilt changes relative to the sun?
Well, the suggestion is it's an artifact of the coordinate system used in diagrams. It's about perspective.
Ah, like drawing it flat on a page.
Sort of. Textbooks often use what's called an orbital frame or ecliptic coordinates. They draw the orbit as a flat line and then show the Earth tilted relative to that line at different points.
Oh.
Visually, this makes it look like the axis itself is changing its angle relative to the orbital plane throughout the year. But in the inertial frame, the one fixed relative to distant stars, the axis tilt itself doesn't change.
So the angle of the axis in space is constant. It's just that as the Earth moves around the sun, the relationship between that fixed axis and the sun changes, creating seasons. The diagram simplifies it in a way that accidentally creates this geometric impossibility.
That's the argument. The simplification, while helpful visually, obscures the inertial reality and implies a physical change, axis reorientation, that isn't actually happening and would violate conservation laws if it did.
So the solstice alignment as depicted requires this impossible axis movement if you take the fixed axis rule seriously. It seems like a case of assuming the conclusion seasons happen because of this alignment without checking if the mechanics of achieving that alignment are physically possible under the other assumptions, like the fixed axis.
That's very close to how the source frames it, identifying a potential logical issue there, like begging the question.
Fascinating. Okay, that's a huge point about geometry and perspective. Let's shift gears smoothly now to the second major point, orbital dynamics. Specifically, Earth's speed changes.
Right. Let's talk velocity. Kepler told us, and we observe, that Earth doesn't orbit at a constant speed. It moves fastest when it's closest to the sun, at perihelion.
And slowest when it's farthest away at aphelion. Everyone knows that part.
Yes, but why it happens is often explained. Well, incorrectly, according to this analysis.
How so? The usual story is gravity, right? Gravity pulls harder when we're closer, so it speeds us up. And then maybe it breaks us somehow on the way out.
That's the popular narrative. Gravity accelerates Earth towards perihelion, implies some kind of forward boost, and then maybe breaks it, heading towards aphelion. It suggests gravity has a component along the path of motion, a tangential component.
Okay.
But that fundamentally misunderstands gravity in this context. Gravitation is a central force. The force vector always points directly along the line, connecting the sun's center and Earth's center, radially inward.
Always pulling straight towards the sun's middle. No sideways push along the orbit.
Exactly. A central force can change the direction of motion. That's what makes the path curve into an ellipse. And it changes the radial component of velocity. But it has zero component along the tangent of the orbit.
So it can't directly push the Earth forward to speed it up or pull it backward to slow it down along the orbital path itself.
Correct. It simply doesn't act in that direction. So the idea that gravity directly causes the speed change by pushing or braking tangentially is, according to this first principle's view, dynamically wrong.
Why do we speed up and slow down if gravity isn't giving it a tangential kick?
It's all about energy conservation and geometry. The total energy of the orbiting Earth kinetic energy plus potential energy has to stay constant.
Right, K plus U is constant.
As Earth moves closer to the sun, lower r, its gravitational potential energy becomes more negative. It decreases significantly. To keep the total energy constant, the kinetic energy, which is half mv squared, must increase.
Ah, so losing potential energy means gaining kinetic energy. Gaining speed is just the system balancing its energy books as the distance changes.
Precisely. It's a passive consequence
Yeah.
of moving within a conservative force field on an elliptical path. The speed change happens because the distance changes, not because gravity is actively pushing or braking along the path.
So the math backs this up.
Absolutely. The Wies-Vieva equation, which gives the orbital speed, shows velocity depends only on the gravitational parameter, gm, the distance r, and the size of the orbit, semi-major axis A. There's no term in there for a tangential force. The speed change is entirely accounted for by the changing r.
That track analogy you mentioned earlier seems perfect here. A frictionless ball on an elliptical track around a central hill. Gravity pulls it towards the center of the hill. As it goes down the steeper part near the hill, it naturally speeds up. As it climbs the shallower slope further away, it naturally slows down.
Exactly.
No one needs to push it sideways. The speed change is just built into the shape of the track and the constant inward pull.
That's the perfect analogy. The narrative that gravity accelerates or brakes tangentially is attributing causation incorrectly. It's mistaking the correlation speed changes with distance, where gravity is the central force for causation, by a non-existent tangential component of that force.
Which the source calls a false cause fallacy. post hoc ergo propter hoc, basically.
Exactly. It identifies that as a key logical error in the popular description.
Okay, these 2 points, the axis geometry and the orbital speed explanation, they really do seem to highlight potential inconsistencies when you apply strict deduction.
Yes. And the sources argue these aren't just minor quibbles or interpretation differences. They claim these are deductive contradictions arising directly from the model's own axioms, like conservation laws and the definition of a central force.
And it connects back to the diagrams again.
It does. The source highlights how frame-dependent visuals, like those ecliptic coordinate diagrams, can inadvertently create illusions, like the illusion of the axis tilting back and forth relative to the plane, or perhaps making it easier to misinterpret gravity's role. They obscure the underlying inertial frame physics.
So the call here is for what? A stricter approach?
Essentially, yes. A call for cosmological modeling to prioritize rigorous deductive derivations from fundamental axioms like conservation of angular momentum and energy over reliance on potentially misleading narratives or simplified frame-dependent visualizations. A truly consistent model needs that solid geometric and energetic foundation.
It suggests we need to be really careful about the difference between a useful teaching model and a description that's fully consistent with fundamental physics in all frames.
That sums it up well.
All right, we've covered a lot of ground, really pulling apart some core assumptions. Let's just quickly recap the main takeaways for everyone listening.
Okay. First, that geometric point. The standard model requires Earth's equator to align with the terminator at solstices. But if the rotation axis is truly fixed relative to distant stars, conserving angular momentum, this alignment is geometrically impossible unless the axis momentarily becomes perpendicular to the orbital plane, zero tilt. That would require a huge, unexplained torque.
Right, so either the axis isn't fixed or the solstice alignment doesn't happen quite the way the simple diagrams imply, a potential contradiction.
Correct. Second, the dynamics. We clarify that gravity, being a purely central force, cannot directly speed up or slow down the Earth along its orbital path.
Yeah, no tangential push or pull.
The observed speed changes are purely a consequence of the conservation of energy within the gravitational potential field, dictated by the changing distance from the Sun. Attributing it to a direct push-pull from gravity is a mischaracterization of false cause.
So where does this leave us? If these analyses pointing out contradictions are valid, what's the implication?
Well, the source suggests that if foundational inconsistencies exist, we need to be open to exploring alternatives or refinements.
Like what?
It could mean rethinking the fixed axis concept, perhaps fixed relative to what? Galactic frames. Or, if the solstice alignment is geometrically precise, then searching for a real physical source for that massive periodic pork, maybe exotic physics, like interactions with dark matter gradients, though that's highly speculative, of course.
Or just acknowledging the limitations of the simplified models we use.
Exactly. It underscores that even established science is, or should be, a constant process of questioning and seeking deeper, unassailable consistency. It's not settled dogma.
Okay, a final thought then, something for you, our listeners, to mull over. Think about those diagrams you learned from the Earth orbiting the Sun, the tilt shown changing relative to the sunlight. Next time you see one, ask yourself, is this showing the physical reality in a fixed reference frame relative to the stars? Or is it a convenient, perhaps even necessary simplification that uses a changing reference frame, the orbit itself, and just might be hiding a deeper geometric or physical puzzle?
A great question to keep in mind.
We'll leave you with that. See you on the next deep dive.